extremely seminal, and most of us have read, tried, and used a lot of his work. He's also been working on robotics with Davison robotics, and so a lot of these things are now perfectly by and technology that you can use in your own research, and I think most of some point have. So, welcome again, Professor Davison.
Thank you. Probably don't need this, do you? Yeah, so thank you very much for the introduction and the invitation. So I'm going to talk to you today about a number of things, but I'm going to fit it in a structure that I think is a kind of argument I've been thinking about a lot recently, about where this whole area of SLAM, semantics, deep learning and everything is going over the next few years, which I think is probably very exciting directions, and I'd like to give you a few of my thoughts on that. So I called my talk from SLAM to spatial AI, and I'll explain a bit about what that means. So whereas the usually stated goal of computer vision is something like to report what is where in an image in a general way, let's talk about this slightly different problem called spatial AI, which is the online problem where vision is to be used, usually alongside other sensors, as part of the artificial intelligence which creates an embodied device to interact usefully with its environment. So, some of the speakers before have really talked about this issue that I think we're at a point now where we've been able to show quite a lot of competence in things like semantic vision. Attention is kind of turning to what it's for, what it can actually enable. So that's something I'm very interested in. So therefore, the goal of a spatial AI system is not abstract scene understanding, but continuously to capture the right information and to build the right representations to enable real-time interpretation and action. So spatial AI is a term that I coined recently. For me, it's a kind of evolution of this thing I've always been thinking of, working on and interested in, which I've mainly called SLAM. I've written a full paper kind of explaining this whole argument, which is summarized in this talk. If you're interested, it's called Future Mapping the Computational Structure of Spatial AI Systems. It's available on archive, and I'd always welcome any feedback on that. So let's try and look a bit ahead about where we might be going with this. So let's imagine some breakthrough spatial AI products for the future. So here's an example, a mass market household robot. So this is a field I'm very interested in. The picture is just a representation I found on the internet. It's nothing specific and nothing to do with Dyson. Get a lot of trouble. Its tasks will include the ability to check whether furniture and objects are moved or changed, to clean surfaces and know when they're clean, to manipulate and tidy arbitrary objects, and to deal promptly and respectfully with humans by assisting them. Its spatial AI system will be constrained by price, aesthetics, size, safety, and power usage, which must fit within the range of a consumer product. So I'd like to get across, this is really general purpose sort of robot. It could do all sorts of things in your imagine a future augmented reality system with the form factor of a standard pair of glasses. It will provide the wearer with a robust real-time overlay and spatial memory of all the places, objects, and people they've encountered, enabling things such as easily finding lost objects, placing a virtual note, or other annotations on any world entity. It will weigh 65 grams and have all-day battery life. So we're really talking about something the size of a standard pair of glasses. It does kind of the whole semantic vision SLAM thing. Okay. So I think these are products which, when they exist, if and when they exist, they'll change the world. They'll just be so useful. They'll be cheap. They'll be robust. People use them all the time. I'm sure about that. And let's think a little more scientifically about where spatial AI is going. So I won't go into these things in detail, but a couple of really interesting, very sort of scientific discussions about artificial intelligence and where it's going, highlighting things like, what's really important in AI are the ability to faithfully simulate real-world environments as the environment changes continually and unexpectedly and much faster than in real time. So we're talking about general AI systems that can really reason in the complicated real world. They need to do the same sorts of things that humans do to come up with a sort of mental picture of the world where you can imagine what will happen if I do this, if I push this, will that object fall over. That kind of reasoning that we're not really close to in current AI systems. So a couple of really interesting references along those lines, again, which are really arguing, I think, for why we need spatial AI if AI is going to go everywhere. So what I'd like to argue is, first of all, that AI and IA, these two things, they need very much the same capabilities from a perception system. So whether or not you're documenting the loop as you do in AR, or you're just building a standalone robot, I think you need very much the same kind of capabilities. And these are some of the kind of things you need: precise, low latency localization, dense predictive local scene modeling, semantic object instance mapping, long-term scene understanding in different changing scenes with very efficient operation on low-cost hardware. And I'd like to argue that we're still miles away from that. And I really think it's all orders of magnitude. So just a little sketch here, we've got kind of products, things we can already buy. We've got certain things going on in the lab which demonstrate more, but probably are working under, requiring a lot more hardware or different constraints. And then we've got where we want to get to over here. And I haven't specified an exact scale here, but it's something like performance in this full kind of spatial AI capability divided by resources required, power, that kind of thing. So it's like rapid progress. I still think we've got a very long way to go in this field, so I have these edge. So the next part of my argument is that this area working is evolving into spatial AI. And you can see some ways that's been happening in some of the talks earlier. We've seen this kind of rise to levels of SLAM, where initially the focus was on localization, where as a device. Increasingly, we're able to show things like dense mapping, actually reconstructing the detailed shape of the world, and now in a very active field of semantic understanding, so building maps that actually also have meaning. So those of us working and thinking, calling out SLAM have generally tried to build systems like that while keeping them robust, real-time, demoable type of systems. And I think that as we build up through this capability, keeping within those kind of constraints and building those kind of systems are the best model I can think of how we're going to get to this full spatial AI capability. So we bring in different capabilities, different things that we try to do, different algorithms from computer vision and beyond, but we build them into this kind of real-time system that has to work. And I think that's the way that we'll gradually step up towards this full capability. So this diagram here is just a simplification of showing some of those capabilities. So here's a hypothesis, which I'd be keen to get people to use on. I think this spatial AI problem has quite a generic character, so whatever the actual application is. So here's a hypothesis: when a device must operate for an extended period of time, carry out a wide variety of tasks, not all necessarily known at design time, and communicate with other entities, including humans, its spatial AI system should build a general and persistent scene representation, which is close to metric 3D geometry, at least locally, and is understandable by humans. So what I mean by that is we can think of lots of different systems that might require spatial AI. So I've already shown you two. There are many others, a drone, an agricultural robot, perhaps. There's many different things. And you can clearly immediately see that different applications will need different levels of capability. They may or may not need detailed semantic understanding. They may or may not need really high-quality metric reconstruction, and something much more kind of topological might be suitable. But I think that there's, rather than those being completely different solutions, those different applications, I think that the general core of how the system works is probably going to be fairly common. It's going to have certain parameters which you would adjust and set depending on exactly how you want those different capabilities to work, depending on your application. But it's got quite a general character, and if we sort of inspect how the system works, we're going to see components, I think, that look a bit like localization, mapping, labeling, recognition, things that we've already kind of names for probably in some sort of structure that will be kind of recognizable. So I'll come back to that one a little bit later. And it is just a hypothesis, it might be wrong. Second hypothesis, very much related to the usefulness of a spatial AI system for a wide range of tasks, is well represented by a relatively small number of performance measures. So we've already got some performance measures for SLAM, like accuracy or efficiency. I think there are going to be other measures which we might consider. I think it's going to be close to 10 or 20 probably useful measures, then hundreds or thousands. So again, another hypothesis. So just a very brief kind of history here to show you a little bit of this progress in SLAM, which I think is building up in the right direction towards spatial AI. So first of all, so really breakthrough work, in my career on enabling real-time vision-based SLAM with a single camera. So this was the mono-SLAM system. So this we first got working in real time in about 2003, and it was a system where we could wave a single camera around the room and reconstruct a map, probably 100 features or something like that. It was joint probabilistic estimation using an extended camera filter, and that was kind of an important step because previous to that, SLAM systems had relied on quite a lot of specialized hardware or assumptions. They'd been on 2D robots, they needed special sensors or even stereo. Here we showed this kind of ultimately simple sensor setup of a single camera connected to a computer with nothing else could do this SLAM thing, and it could enable localization. So that's really what the focus was here. It was just about estimating the position of the camera, and we demonstrated things like doing augmented reality with that system. So there were many developments based on that, including things like the PTAM algorithm from George Klein that was mentioned earlier, ended up being the basis for Microsoft HoloLens, for instance. The next big sort of real step forward or revolution, I think, was when we started working on dense SLAM. So this was around 2009, 2010. Daniel already showed some work in this area. Really important in driving that work was Richard Newcomb, who was in my lab at that time. He did work on high-density reconstruction, showing that we use GPUs in particular as part of a real-time vision system to do this sort of real-time vision where you reconstruct something at every cell, at every frame. So rather than having to extract just sparse features from an image and reconstruct those, he was estimating the depth of every pixel in an image. We moved on to develop a system called DTAN, where we showed that once you were building a nice dense reconstruction of the scene, you could actually turn off any feature-based tracking and just track the camera against that reconstruction. So that was the DTAN system that later on led to things like LSD-SLAM that led to Daniel was showing you earlier, so a dense-only system. And then another very important technology that emerged at the same time was commodity low-cost depth cameras like Kinect, and worked on Computer Vision that was able to do real-time dense mapping using Kinect cameras. So also led to a lot of follow-up work. So I'll just quickly show you this video. This is relatively recently from our lab system called Elastic Fusion. So quite similar in many ways to some of the things that you've seen from Andre, from Stuart, from Daniel in the talks earlier. So it's a real-time dense SLAM system using a handheld depth camera. Here the kind of central point is that we're using a circle-based representation, and it's a real-time blue closure capable system that's pretty good at mapping room size scenes. So it is not something that's mapping whole buildings, but it's an efficient way of mapping rooms. So this running on the GPU will be easy. So that's a very current dense SLAM system. And then really the thing that me and a lot of people are working on recently, this is also very similar to some things that you've already seen, a system called Semantic Fusion, which is a system that actually does a relatively straightforward combination of a dense SLAM system. So Elastic Fusion, I just showed you, which builds a map of cells, and then a CNN, which is taking input frames, labeling them with a kind of off-the-shelf semantic segmentation, but then fusing, so projecting those labeled frames back out into the 3D model and labeling the circles. So each circle in our map is holding distribution over these possible classes, which gets updated over time. So as our camera is browsing the scene, and we're being focused on indoor scenes here, each circle gradually, hopefully, builds up a better and better estimate of the type of surface that it's part of. And you can see the sort of level of performance we get. It's okay. It's a bit messy, and importantly, we're not really finding objects here. We're just labeling surfaces by kind of painting semantic labels onto them. This may be useful for something, or it is probably useful for local avoidance or something, but it's not going to enable really detailed interaction yet. Okay, so what we already have out there right now are certain products and systems. So these are things you can actually buy, which are SLAM-enabled products in several areas. So there's home robotics. So Davison I've particularly been working with, and other companies also have robots that use SLAM in order to do positioning. There are various systems now where SLAM runs on smartphone devices. So there was an original project from Google called Project Tango, which was quite influential. They actually designed a sort of specific phone architecture to the idea for SLAM, and then they did a lot of the development and fed that into now systems that run more standard phones. So AR Core is Google's effort there, AR Kit is Apple's version. So this is basically SLAM on a smartphone. It uses the camera and the IU on a smartphone, so you can move around and it will track its position, and you can do things like augmented reality, in the room on a desktop using those systems. Microsoft HoloLens is an augmented reality system, probably the best one that's actually out there and you can get at the moment from Microsoft. It has a stunningly good tracking system and special display, so it's see-through augmented reality, and SLAM is all about tracking the user's position really, really accurately so that you can place virtual models in the scene. It does some sort of dense mapping. It uses a depth camera to build a sort of fairly rough density reconstruction of the space. There's a little bit of semantic understanding in that it can recognize surfaces and planes and so on and affix virtual elements to certain meaningful things in the scene. And then another area of interest is the drones. So DJI, for instance, is an amazing company in China that makes some of, I think, the most widespread consumer drones now. They have actually quite impressive onboard some capability. Skydio is an impressive company in the US that's doing some of the things. So positioning and spatial semi-dense reconstruction is the key technology behind most of these that's enabling the positioning capability. That's relatively mature, but still definitely a lot of room for improvement. It's enabling real products. And then some level of dense and semantic mapping are being developed for these products, and we can expect there to be progress in that quickly. So just to look at this one a little more, because I personally worked on this. So Davison first approached me in 2004 to say that they were interested in building a vision-enabled robot vacuum cleaner, and I worked with them as a consultant for nearly 10 years, it turned out, on designing what ended up being this product. A long time and testing and so on. So I continue to work with Davison. What I do now is I run the Davison Robotics Lab at Imperial College, where we're really looking in a much more forward-looking way at general vision technologies for home robotics. So certainly now very much beyond vacuum cleaning towards general home robotics. So there are products out there, but I would say these are still sort of tester products at the moment. They're not going to change the world yet. They're expensive, so both in terms of cost, also in terms of their kind of requirements. The battery life is not very good, that kind of thing. They're not super robust, and they're a bit limited in the number of different things that they can do. So something that I very much observed over the years is rising computer power. We've been able to throw more and more computing, both in PCs and embedded devices at Computer Vision over the years. It's enabled us to do more and more. But that comes generally as a cost in terms of needing more power, especially for the processing. So I think these are still sort of tester products in terms of where we need to get to in spatial AI. How are we going to get further? So I think that we need to kind of go back a little bit to think about this spatial AI problem a bit from scratch. So this is the kind of setup. We've got the sensors, so cameras and possible other sensors, receiving data, and then feeding into some kind of representation that the device keeps about the world. So we'll call this the world model, and this includes things such as the position, estimated position of a robot, the shape of the world, the identity of semantic elements and objects. And we can think of this sort of layered system that builds those things up in quite a separate way. But I think if we think about that world model in a more integrated way, that might be the route to both higher performance and eventually to more efficiency. So the world model has many aspects, but there are huge advantages when all of these can work together and help each other. So just to give you an illustration of what I mean by that. So this was a paper that we wrote back in 2013. So the lead author was Renato Salas Moreno, who's a PhD student in our lab. So this is a SLAM system, but which builds a map directly at the level of objects. So if I show you this video, so it's kind of the same setup as in Connect Fusion or Elastic Fusion, in that we've got a handheld depth camera moving around a scene. But what we're not going to do is a bottom-up, dense 3D reconstruction of the scene. Instead, we're going to take advantage of the fact that we have prior knowledge that a certain set of objects will be present in this scene. So in fact, in this system, it's a really rather precise database of objects. And we actually have 3D models of the chairs and the tables and some other objects that we know are present in this particular scene. And they really are very precise 3D models. We scan them with Connect Fusion, and it really is, this model is this type of chair, this is this type of table, I think. So basically, as the camera's browsing around, it's not doing any immediate reconstruction, but it's running object detection. So it's using its depth image, and it's scanning that continuously to try and find instances of any of these 3D objects. And when it finds one of the objects, it brings in its high-quality 3D model of that object, it aligns it with the depth image, and then if it's got a good enough agreement, it then just pops it into the map. So this is the map here. It exists at the level of objects. There's no other kind of representation. So we don't know anything about parts of the scene that aren't those objects, but the things that are those objects, we know in excellent detail. We have full semantic meaning, we have their full 3D pose. And then the way the SLAM system works then actually uses relatively standard SLAM ideas in that it builds a pose graph. So this means it's a graph. Every time you observe an object from a position of the camera, you've got a constraint that says, from this observation, I know that the relative position of this position of the camera and this object has this 6-degree freedom constraint. And then we've got a whole graph. I've seen this object from multiple positions, so lots of constraints. There's also some kind of weak temporal constraints between positions of the camera. And then we can optimize that and do loop closure and do all the normal sorts of SLAM things. And so you can think of it a little bit like each object is a bit like a super feature. It's a little bit like going back to the point features we had in our original SLAM system. Each point is an object. This is just another little illustration of the great advantage of immediately recognizing objects. So this shows something about how we search for new object detections. And we tried various methods for these, including random forest. This was sort of pre-CNN. But the important part here is to look at the red samples. So these are the places in the image that we're randomly sampling to try and look for new objects. So when we don't know about any objects in the scene, those are spread evenly over the whole image. But once we pop a few objects into our map, we only need to search the parts of the scene that we don't yet have good object models for. So we get this now very sort of efficient, focused search in the areas that we don't yet understand. So we really sort of got a real feedback going on there between our understanding of the scene and the actual amount of processing work that we need to do. So I think that's just a kind of flavour of how I think if we're bringing all of these elements of geometry and semantics and representation together, then we can do things which are effective and efficient. Another very closely related piece of work, so that also by Renato, was on dense planar SLAM. So this is another example of bringing kind of assumptions to the fore. So if you know that your scene contains lots of planar areas, then recognize those planar areas. So here we did map single circles, but once we detect a planar area, we kind of fix all of those circles to be exactly planar, and we can represent that area in a much more efficient way than general 3D circle cloud, and we get this nice semantically kind of labeled meaningful representation of the scene. So one of the demos that we did with this was, put your Facebook wall on a real wall in your house that you recognize with this dense planar SLAM system. Okay, so clearly now, if we're thinking about building systems like this that have elements of geometry, semantics, everything kind of working together, you immediately think about deep learning. And a very tempting question to ask is, could we replace whole kind of complicated systems that include elements of geometry and learning a single network learned end-to-end? So just as a little illustration, this was just a a not very careful attempt at thinking about the sorts of computation that's involved in a system like semantic fusion, where you've got lots of different computation elements. You've got images coming in, you've got your world model, you've got your sort of camera state, and you've got all the different sorts of processing that you do. You track, you fuse, you get your labels from your image, you fuse your labels. So this is the kind of tracking loop where you iterate over tracking error and so on. It's a pretty complicated sort of modular system. So it's pretty tempting to think, could you just replace all of that with a single network and end-to-end? And maybe eventually we will. So what something I'd like to argue is I think there's actually a real sliding scale between something like this block diagram here, a fully kind of human-designed structure of lots of different computational elements, versus something that might just be a single neural network that takes images in and outputs some kind of estimation or action. Those are two ends of a scale, in the middle of which there are lots of other options. So I think every time you take a neural network and design some kind of structure into it, that's somewhere along this scale, or every time you take a kind of design system and put a neural network into it, somehow that's also somewhere on the scale. But there's many options. And I think lots of the most interesting research in the next few years is going to be what are the right options there. So in fact, at CVPR, just a month or so ago, we ran a workshop on deep learning for SLAM, which was amazingly popular. There were people kind of bursting out the doors. We had a room for 300 or 400 people, and it wasn't big enough. And we had a lot of discussion about these kind of things. And there was a nice comment from Sir Jitendra Malik, one of the most famous researchers in computer vision. I pretty much asked him this question, what are the right things to choose? So what are we allowed to assume if we're going to start designing a structure in neural networks? So presumably a pure deep learning person would say don't assume anything. Allow your system to discover whatever representation it needs to enable the task. But Jitendra said, why don't we hard code things and then use this phrase, God's own truths? So particularly something like, our understanding of 3D geometry is a pretty solid thing that we understand, or physics, the physics of rigid bodies or something, or just the simple fact that the world tends to consist of separated objects. Why would you learn that from scratch again and again rather than sort of designing in? So maybe that's almost a philosophical point. It seems like humans, in the end, if our intelligence has evolved, have somehow discovered these concepts. Maybe they're kind of baked in through evolutionary time or something like that into our brains. Anyways, but most research is proceeding in a modular fashion now, with varying degrees of assumptions and models, somewhere on this sliding scale. So, I would say there are two key ways to think of combining design and learning. One is to have essentially a neural network, but within that neural network to design certain blocks which sort of force the network to work in certain ways. So one example is a library called GVNN, which was released by my former student postdoc, Ankor Handa. It includes sorts of spatial transformer blocks and things like that. The other approach is just to build more kind of modular systems. So something like Semantic Fusion, it has designed SLAM components, but then it uses neural networks in certain places. So something that's really exciting at the moment is we're seeing neural networks that are doing all kinds of interesting things. So whereas it was always obvious to me that something like recognition or semantic labeling, that's a good job for a neural network, we never really knew a very good way to do that with neural networks. But now we're seeing neural networks doing remarkable things in areas like geometrical vision, where we do have pretty good methods already. So things like optical flow estimation from a pair of images. Daniel was one of the co-authors on this FlowNet work. Visual odometry, so here's a pair of images, estimate the relative motion between those two images. There's neural networks that do a pretty good job on that. Depth estimation from a single image also starting to work really well. So I expect that when I talk about modularity in these systems now, it's we may be very quickly replacing elements like these as well with living elements and figuring out how they all fit together. So my observation about these kind of methods at the moment, they certainly seem to be very good at robustness, certainly in circumstances good, close to their training sets, so they'll nearly always give you something fairly sensible. Accuracy still seems a bit harder to achieve, so getting really accurate visual odometry or depth estimation from a neural network still seems hard. And it's definitely notable that SLAM and geometrical vision is an area that has not yet been totally swept away by deep learning. The designed methods in certain problems are still holding on really well. So will we eventually get this kind of full end-to-end learning for spatial AI, maybe eventually trained purely on reinforcement awards? So yes, maybe, but I think going back to my earlier hypothesis, if we really want a system to do a wide range of things that we expect of something like a general-purpose home robot or an advanced AR system, within that large neural architecture, we would probably find something which is quite recognizable as a locally close to metric map. So therefore, maybe we might still design it. So I think that even if you did train it end-to-end, maybe it would learn something that would be quite similar to what you might start using. Again, our hypothesis, which could be wrong. So another big area, if you're bringing deep learning into spatial AI, where does the training data come from? There's tons of things going on in that area. I think there's three kind of key options that are interesting. There's supervised data sets. So this is ScanNet, for instance. The trouble with that is how do you scale it without an incredible amount of human effort. The simulation, so this is a really interesting thing. You just simulate scenes that look real, but with the great advantage that you can get ground truth for free. So this is our project called SceneNet RGBD, where we generate these kind of closer photorealistic video of indoor scenes flushed with random objects, but where we've got ground truth on everything because it's just generated with computer graphics. We've got ground truth depth, object segmentation, object instance, and so on. And then another really exciting area at the moment is self-supervision with geometrical learning. So there are a couple of really interesting papers recently showing how, for instance, if you're training a network to predict visual odometry and another network to predict depth from a single image, you can actually use those to kind of train each other by kind of fighting against each other and aiming to minimize the vector consistency loss. And that's an area where I think SLAM can be increasingly important, because a SLAM system is essentially a correspondence engine. It can provide exactly the right sort of data that you need for training your network. So for instance, to do something like recognize an object from arbitrary viewpoints, if you've got a SLAM system and it's able to project that object into an arbitrary number of views from different viewpoints, different lighting, you could capture exactly the right data that you might need. So I think there's a thing that deep learning helps SLAM, but I'd emphasize SLAM helps deep learning as well, and let's really bring those things together. So I'm interested in even like, could you be self-supervised segmentation, like that, something like that. I think there are good possible ideas for that. Okay, so to move on to something a little bit different, but hopefully you'll see how it's related. So I talked about these real products that we want to get to and how the constraints of real products like power efficiency are super important. So these are just a couple of examples. So Google Glass from a couple of years ago, I think if you ran the video camera, it got so hot within a couple of minutes, you had to take it off your head. We've had a project, so this has been a joint project called Pamela with the universities of Manchester, Edinburgh, Imperial, really investigating what happens to SLAM algorithms when you run them on different sorts of processors. So here we're running Connect Fusion on everything from a big desktop GPU down to a tiny embedded board, and we really analyze what happens to the performance of the algorithm. We look at all the different elements of the algorithm, which parts scale up and down nicely, which parts benefit from parallelism and which don't. So we hope this is opening up research on joint development of real-time algorithms, programming tools, and also architecture. So a big message for me for spatial AI is I think if we want to get all the way there, we're going to have to think about sensors, processors, and algorithms in a much more kind of coherent way. So we've also recently, so SlamBench is this original project. There's a new project called SlamBench 2.0, which makes this a much more general and flexible thing. So it might be a very useful thing to you if you're interested in testing some algorithms. So those were off-the-shelf processors, but there are really interesting, more kind of forward-looking things going on in computer architecture that I think are really relevant to spatial AI. And really this argument that we've been using processors that weren't designed for vision, they weren't designed for AI. So CPUs were designed for general purpose computing, GPUs were designed for graphics. Why not design processors that are really suited to the workload that we have in AI? A particular company to focus on that I think is really interesting is GraphCore, which is a startup company based in Bristol. They really say that CPUs or GPUs aren't really well suited to the workloads that we have in AI, which you can very often think of as sparse graph type of algorithms. And when I think about SLAM, this makes sense to me. So if you have a processor which, instead of being dominated by logic with a small amount of memory like today's GPU has a a relatively small amount of logic, but embedded in a kind of huge memory substrate, which enables lots of independent processors to run quite sort of independent programs, but with massive memory interconnect. They can implement a certain sort of algorithms, which are message passing algorithms, very, very efficiently. So the key idea is to bring the memory and the processing together. So rather than having to always send and fetch between processor and memory, it's like organize your algorithm and your data structure in a coherent way so that you're not moving data around very much. And that is a potential way to get really low power. So it's going to require rethinking all of our algorithms and everything, but I think this is a really good long-term direction. So this is a nice visualization from graph where it shows the output of they have a graph compiler. So actually what they're currently mainly targeting is deep learning accelerators for the cloud. So they can take a deep network. I think this is AlexNet, the original kind of image net recognition classification algorithm. They look at all the kind of elemental computations that make out what AlexNet does, both in the forward pass and during training. And then if you kind of zoom out enough on that computation graph and visualize it in a nice, cool way and splat it onto a disk, you get something that looks a bit like this, where it's showing the connectivity of all the different computations that have got to happen. And it looks a bit like a brain, maybe, or something. But I think that's very interesting. So if we want to make SLAM efficient, if we want to make it run these type of processes, I think we need to find the graphs in spatial AI. And I think there are certain elements of SLAM and spatial AI where we can immediately see these graphs. So there's a graph in our image data. There's this kind of regular grid, and nearby pixels tend to be kind of related to each other, the same sort of assumptions that make CNNs work well, or CRFs or things like that. There's the map graph, so I think a lot of work in SLAM, Cyril here has been behind a lot of that, showing that kind of graph structures in SLAM are really fundamental and the right way to represent kind of locality in the map that the SLAM system makes. And then we've got kind of processing graphs. So like the picture I showed you earlier with the yellow blocks all connected to each other, this is a processing graph showing how different elements of processing in the system relate to each other. So this is just a very first sketch attempt that I made of drawing a kind of equivalent to that graph or brain for the spatial AI problem. So we've got these different graphs. We've got cameras connected over here, and I think something else that might be happening in this long-term spatialized AI system is these cameras will do a certain amount of processing themselves. So there are prototypes for cameras that kind of have in-plane processing. They do certain amounts of stuff before they send data to the main processor. So our work on event cameras is very much in this area, I think. We've got this real-time loop embedded here, receiving data from the cameras, doing some processing, and relating it to our map store. So this is just a sketch, and there's so many things to be worked out here. But I think there's certain processing, so certain elements of what goes on in spatial AI, which we can think of mapping to different parts of this structure. So in the close sensor processing, this is pretty much the feed-forward stuff mainly that happens to every image. So things like local motion estimation, optical flow, sort of segmentation or labeling of an input image, detecting features. Probably some multi-purpose CNN that does various and interesting things. We've got our real-time loop, which is doing the main sort of frame rate sort of tracking loop, predicting views, tracking against a map, locally updating geometry. And then we've got our map store. So I think this is running certain amounts of computation that sort of live with the map naturally. So I think things like loop closure detection, loop closure correction, they can sort of be embedded within the map themselves, I think. So regularization and smoothing, maybe things like unsupervised learning, clustering to discover new semantic categories. So very graph-like operations. So a real difficult issue, I think, is how do we connect the real-time loop and this kind of map structure? Because in a SLAM system, the camera or other devices moving around, so you've got this connection between the sensor and the map, which is dynamically changing, and maybe we need to invent some kind of router node or special process to continuously keep that properly connected. Okay, so the last main thing that I'd like to talk about is some new work from our lab, which I think is a bit of a prototype. So given that I think we've argued that we need to think about representation in mapping and SLAM, we need to think about new ideas, we need to think about how geometry and learning come together. So let me just quickly switch to some different slides here. So this is some work that we just presented at CPR called Code Slam, which is a new sort of representation. So in bringing learning and geometry together here, so rather than sort of keeping an existing SLAM representation and then using networks to do some processing on that, what we're doing here is we're using a neural network to redefine what our representation is, and then we're running fairly standard kind of geometric optimization methods on that representation. So just to explain what that means, so we've particularly come up with a representation which we think has some of the advantages of both sparse SLAM representations and dense SLAM representations. So sparse key points, you have the big advantage that you've got a very efficient representation. You're representing a room with a fairly small set of numbers. And another great advantage is you can properly probabilistically reason about that. So in particular in SLAM, we're very interested in this capability to jointly optimize the motion of the camera and the structure of the scene. So this is what it happens in bundle adjustment. This is kind of what a camera filter does sequentially. So this whole fact that as a camera moves around and makes a map of the world, your estimates of where the cameras are and where the map is have been correlated together. And if you want to get the best possible estimates of both of those things, you have to jointly optimize. So in dense SLAM systems, we have a much better ability to represent the shape of the scene in a really detailed way. You can't in a sparse system. But what we've kind of traded off or lost in order to do that is this ability to efficiently and jointly optimize our representation of the scene. So the way that dense SLAM systems like Net Fusion or DTAM generally work is a sort of coordination. So rather than joint estimating motion and shape, you kind of assume the shape is correct and estimate motion, and then you assume the motion is correct and estimate the shape, and you kind of alternate those two things. So it's not quite probabilistically correct. So to show you how we've got a new representation that sort of tries to bridge that. So first of all, let's just look at some depth data. So this is actually synthetic data. So imagine a depth camera moving around and looking at this scene, and you can see the depth maps that are captured. And the important and obvious thing is that there's a huge amount of spatial structure in these depth maps. They're very much not just random noise. So the real world consists generally of coherent objects and structures, and the way that cameras move through those worlds smooth. So what this immediately makes you think of in a learning setting is something like an autoencoder. So this is this bottleneck type of network where if you show it lots and lots of examples of real-world depth images and then use an autoencoder which uses a network that has a bottleneck but tries to reconstruct things that look the same as the input but forces it through this small amount of numbers. So this is a code, it might be 128 or 256 float values. Can we learn a kind of efficient coding for the amount of variation that we see in the world of depth images? So that's the basic element of our system. But what we find is that if we just do that, we can only get quite fuzzy depth reconstructions of the scene. So we use this extra piece of information that we do have images around. So if we're building a SLAM system, and we're mainly thinking of a keyframe like SLAM system here, we're trying to estimate the depth of each keyframe. We also have the images around. So there's a lot of extra spatial gradient information available in the image. So we'll build a depth encoder, a depth autoencoder, but we'll also condition it on a simple network here, which takes features from an image. And using that, we're able to get higher quality reconstruction. So another nice way to think about this is that we know we have networks that can do a pretty good job of predicting depth from a single image. This system does that, so when we feed in a single image, so imagine this part, at runtime we don't have this ground truth depth, which is just kind of this part of the network. We feed in an image, we immediately get a depth prediction, but then we also have this code available that allows us to adjust it. So in fact, depth from a single image is reasonably good at predicting details, but it's not necessarily that good at getting the gross shape correct. So actually, let's get to this one. This is what this allows us to do. So given that we've got this depth prediction from a single image, we've also got this code, a set of parameters, which we can then adjust to play around with this depth prediction. And you'll see that as we adjust just arbitrary parameters of our code, they cause this depth prediction to change in nice, interesting, smooth ways, which are kind of somewhat close to being semantic elements of the scene. also have this code. So then what we can do is jointly optimize for the estimated positions of the cameras and the code of each image. And our optimization target is photo consistency. So we want to predict the depth map for this image and the depth map for this image such that when we walk through the relative transformation, the pixels line up as well as possible. So here we can see examples of this working. So here's just a two-view case to start with. So here are two images that are slightly different, and we optimize the codes in relative motion. You can see it happening in 3D, and we're able to then estimate the dense shape of the scene. And then here's it working now on about 10 images. So this is from the Europe. This is a real image data set. So we have 10 frames. Initially, we start with a sort of null hypothesis that all the images were taken in the same place. But by jointly optimizing the camera poses and the codes, we can kind of unpack that into this quite nice reconstruction. And then here's an example where we turn this into a simple kind of 5-frame visual odometry system. So we just take the last 5 frames from the camera. So just to emphasize, this is a mono-only system, so we don't use any just mono meaning that there's no depth images, it's just color images coming into the system. But then we're taking the last 5 frames, we're jointly optimizing for the relative motion and for the codes, and we can produce this sort of visual odometry type of thing that produces dense scene reconstruction as well. So it's certainly not yet anything that looks really accurate or completely compelling, but I think as a prototype idea for a new sort of representation, it's very promising. Okay, so just to round up, so I think the sort of map that we're trying to get to some kind of scalable graph of features, either in the 3D world or in a post-graph model. And I think this idea of map representation, what's the right way to do it, that's the most interesting and the hardest problem in spatial AI. I think we should be trying to build representations where the degree of metric fidelity might be a controllable thing. So at one end of the scene, we might have a fully geometrically precise map that when we run our fullest computation, we get that. At the other end of the scene, might back up to something much more like a topological map. And maybe it does things like it only retains maximum quality representation of just the semantics in a focused local map. So a bit like our impression of being human. When I'm looking at this code right now, I feel like I have a really solid 3D feel of its shape. But as soon as I look away, that sort of fades away to something. I don't completely forget it, but I haven't remembered all that detail. How can we build that kind of thing into our systems? Okay, so just to summary, so I think there's some really, let's do spatial AI research. There are some really interesting things to work on, like efficient representations, the path to true SLAM where the objects are the map, visual sensors for vision, not photography or video. So let's think of processor design for this. Let's think of sensors designed for this. So things like event cameras are good steps in that direction, I think. Co-design of processor architectures and algorithms, and graph-based algorithms for estimation. So I'm very interested in belief propagation and things in machine learning like graph networks. So again, if you're interested, please have a look at this paper here. And also just to briefly mention, so alongside my university activities, I'm also co-founder of SAMcore, which is a startup based here in London working on applied SAM solutions. We now have quite a decent-sized team and a lot of exciting things going on. So we're hiring, so please get in touch and interested in that. Okay, I'll finish there. Thank you.